Applications of effective atomic number. As I told in the beginning, this EAN rule it's help to predict magnetic properties of a complex. If any complexes obey EAN rule, it is diamagnetic. If it is not obey EAN rule, it is paramagnetic. So for example, if you just look at the examples here, we know that if any complexes to be act as paramagnetic, the essential condition is it must contain unpaired electron. Or if all the electrons are paired up, so the spin moment is zero. At that moment, it is diamagnetic. You know spin only formula, and you know the basic reason behind magnetic properties of a coordination complexes: spin magnetic moment, orbital magnetic moment. So these are the concept you already understood before. That's why I am not going to discuss in detail. So here you just look at the complex here. You just look at the complex here. So you take the first complex here. So its effective atomic number is 36. Here all the electrons, all the d orbitals, so are completely filled by only two electrons. There are no unpaired electrons present in this complex. If you apply the valence bond theory, and if you write the electronic configuration of hybridized orbital, there you can find the number of unpaired electrons. So here in these complexes there are no unpaired electrons because it is stable. It has 36 electrons and it not containing unpaired electron. That's why it is diamagnetic in nature. That means it obeys EN rule. Why? Because the effective atomic number is exactly equal to atomic number of next nearest noble gases. And if you take this complex, for example 35, here EAN is 35. So chromium complex, chromium 3 complexes, here one unpaired electron is present. So that's why it is paramagnetic. Unpaired electrons are still present. That's why it is paramagnetic. Okay. So based on this, if anything obeys EAN rule, it is diamagnetic. So otherwise, it is paramagnetic in nature. So now, stereochemistry of coordination compound. Stereochemistry means it's a spatial arrangement of ligand around a central metal ion. It is called as a stereochemistry. Stereochemistry just explains how the ligands are arranged around the central metal atom. These ligands arranged around the central metal atom to give a proper definite geometry. The geometry of a coordination complex it depends on its coordination number. So we know that coordination complexes form from 2 to 9 coordination number. Among the most familiar complexes are complexes having coordination number 4 and 6. So totally the geometry, the arrangements of the ligands, the geometry of the complex, it depends on the coordination number. So now let us start from the coordination number 2. You just observe the diagram here. Okay, so coordination number 2 means only two monodentate ligands are present. So dichloro cuprate complex, so diamino complex. So in this case, so the most probable geometry of a coordination complex of coordination number 2 is linear shape. So these are linear of bond angle 180. So usually these type of complexes formed by the complex containing a simple metal ion copper, silver, gold, and so these are the central metal ion usually form a linear complexes. Now let us see the complexes of coordination number 3. So there are three monodentate ligands are present. In this case, the expected geometry is trigonal planar. That means a central metal atom and three ligands present in a one plane. and it has triangular shape and all are present in a single plane. That's why it is called as trigonal planar, and the bond angle is 120 degree. So all the bonds are equivalent 120 degree. Usually this iodo-mercurate complex is the best example for so coordination number 3. Usually the coordination number 3 complexes are rare. Next, coordination number 4. The complexes having coordination number 4. Here two types of geometries are possible. One is tetrahedral geometry and square planar geometry. The nature of geometry is depends on the nature of hybridization. To form a coordination number 4, we need minimum 4 monodentate ligands. This tetrahedral geometry formed if the central metal ion undergo sp3 hybridization. You know, the standard geometry of sp3 hybridized compound is tetrahedral. So that means the 4 ligands are present at 4 corners of the tetrahedron, and the metal which is present at the center. The bond angle is 109 degree 5 minute. So usually the zinc, tetrachlorozinc and tetracyanocuprate and this is X is nothing but it's a halogen. So tetrachloro iron. So these are the complexes. So which is having sp3 hybridization and of geometry is tetrahedral. Next one is square planar complexes. So here if the complex undergo dsp2 hybridization, why the geometry is different? In each case of hybridization, the number of orbital participation is going to be different. That's why the geometry is going to be different. Square planar means here one metal which is present in the center and 4 ligands occupy the 4 corners of the square, and the bond angle in this case is 90 degree. The example for this, these are the example of a compound form square planar complexes. Next, coordination number 5. Here also two geometries are possible. One is trigonal bipyramidal and square pyramidal. So first take trigonal bipyramidal. In this trigonal bipyramidal, the central metal ion which is present at the center and 3 ligands present in a trigonal planar, so triangular, and one is above the plane and other one is below the plane. That means if you consider this is a plane, so one pyramid is present above the plane, another one is another pyramidal shape which is present below this triangular planar. That means two pyramids are present. That's why so it is called as trigonal. So trigonal, this is trigonal and bipyramidal shape, trigonal bipyramidal geometry. The example, these are the examples of so complexes having trigonal bipyramidal geometry. And next one is square pyramidal geometry. Square pyramidal means in this case, so the 4 ligand present at 4 corners of the square and the central metal atom present exactly at the midpoint of the square, but one ligand which is present above the plane and it form a single pyramid, a pyramidal shape. So that's why so this is called as one pyramid which is present on the square. That's why it is a square pyramidal geometry. That means if a complex form 5 monodentate ligand, that means if the coordination number is 5, there are 2 geometries are possible. One is trigonal bipyramidal geometry and square pyramidal geometry. Next, most familiar form of coordination compound is coordination number 6. Here the expected geometry, the standard geometry, the regular geometry is so octahedral geometry. So in this case, so the central metal ion present at the center and 6 ligands present at the 6 corners of octahedron. So they see this picture. This is a 3D picture. This is 3D picture of this octahedral geometry. That is, so finally the spatial arrangements of ligand around the central metal ion, it is depends on the coordination number. If the coordination number varies, the geometries varies. Sometimes that geometry get distorted, so it is called as distorted geometry. That means it is different from the regular geometry. So you just look at, sometimes due to some anomalous phenomena, some standard geometry distorted into some irregular geometry. For example, here hexagonal. So this hexagonal, okay, geometry distorted and it form so trigonal prismatic geometry. Or sometimes, so this is a leaf, if a coordination number is 2, it form linear. If there is any repulsion or any anomalous effects are present around the central metal ion, so instead of linear, it form bent shape structure. So this is how the geometries are varies